So let's go through what this is actually telling us. Let's use purple. So if we increase the temperature, okay, so we're manipulating this variable right here. Okay, we're manipulating this temperature right here. If we increase the temperature, it makes the exponent a smaller negative number. Makes the exponent a smaller negative number. Okay, so if this increases, okay, this number gets smaller and smaller, and it becomes less and less negative. So what that does is it increases the K. Okay, so if this is getting smaller and smaller and smaller, that means this has to be getting bigger and bigger and bigger. All right, so if our constant is getting bigger, what that does, it's going to increase our reaction rate. So a high temperature will always result in a large rate constant. Okay, which gives us a faster rate. So if we look at rate equals K times, I don't know, A to the M, B to the N. All right, so if this is getting big, if this is getting large, okay, it's going to increase our rate. So these two formulas are really interrelated. So this K that we're talking about here is the rate constant that we're talking about here. All right, so if our temperature is going up, that's increasing our K. If our K is increasing, that means our rate is also increasing. Right, so that's what this equation is saying. Now, there's a second part to this, and I need to go to a different page. So let's write that equation out again. So we know that K is equal to that proportion constant to the negative EA divided by RT. Okay, so there's a second thing that's actually happening here. What if our activation energy is increasing? So if our activation energy is increasing, okay, it makes this exponent larger. Makes it a bigger negative number. If this is a bigger negative exponent, what does that do to my K? Well, it's going to make it smaller. Okay, it's going to make it smaller, which means our reaction is going to go slower. Okay, so if we increase the activation energy, this makes the exponent a larger negative number. Okay, this gives us a smaller rate constant. which means we're going to have a slower rate of reaction. So to kind of summarize that, as our activation energy increases, our reaction is slower. Right? And this is just giving, we already knew that, but this is just giving us our mathematical relationship. All right, so let's just compare two things. All right, so let's compare this potential energy diagram with that potential energy diagram. Okay, so remember that this is our activation energy. This distance right here is EA. Which one of these is going to go faster? Okay, well, this one's gonna go faster over here because we only need a little bit of activation energy to get it started. Okay, this is going to need more energy. All right, so as we increase this activation energy, the reaction is going to go slower. Right, so what this Arrhenius equation does is it just gives us this mathematical relationship between activation energy and our rate constant. Right. Now, like I said earlier, we're not going to use this. All right. I may ask you to explain this. I may say, hey, what happens mathematically in this Arrhenius equation with activation energy or with temp? Right. So you don't have to know what this proportion constant is. You're not going to be solving with this equation. You're just going to have to be able to understand what this equation is telling me. And that's it. All right. So there's nothing else with that. Okay. All right, that's where we're going to stop for today. And next class, we're going to continue on with kinetics. We're starting to get through a lot of the kinetics material, but this is going to go right into equilibrium too. So we'll just keep plugging away. You guys are doing a great job. Keep working hard. I really do appreciate all the work that you guys do. I know it's a lot, all right, but hang in there. We're coming down to the wire here. We got a couple months left. All right, you guys are doing a great job. All right, so we'll talk to you next time. Have a good one.